In this video, I'm going to quickly go through the idea of electromagnetic spectrum. So to begin, we talk about something called electromagnetic radiation. So electromagnetic radiation has two personalities. So it sometimes behaves like wave and sometimes behave like particles. I'm sure some of you guys might have heard of this from quantum mechanics, like our understanding of the particles, that particles has this what we call a wave particle duality. And in this case, we call these electromagnetic radiation, these particles photons. And the term particles might make you think that they are like physical round particles, but it's also important to remember that they exhibit wave-like behavior too. But since in most radiative processes in stars in our astronomy, like atomic observation of a photon, radiation will almost always act like a photon. So act sort of like a particle rather than a wave. So in my videos, when I draw a photon, I would simply draw it like a particle, like this. Right? So we went through, so now we get an understanding of a photon. So it's basically these light particles. So now we begin to look at what is the energy of a photon. Well, there's a formula which says E. So E stands for the energy of the photon. So let's make that clear. Energy of photon is equal to H times V, which is then equal to H times C divided by lambda. So what do these terms mean? Well, first of all, you have the Planck constant, which is the H here. So right, we have two H here. They're both the same constant. So H. So what is H? H is the Planck constant, and then its value is 6.626 times 10 to the negative 34 joules, I think. And then we also have another constant in here, which is the speed of light. So speed of light is how fast the speed of light is how fast, like let's say the light travels. Obviously, right? We have like speed of light as 3 times 10 to the power of 8 meter per second. And those are the two constant in the equation. So what are V then? Our V is going to be the frequency of our light. And our lambda is going to be the wavelength. So what do these terms mean, right? So the energy a photon carries. So what does this formula tell us first? Well, it tells us that the energy a photon carries is directly proportional to the frequency of the photon, right? If we have the formula E equals to H times V, if H is constant, then the only changing variable in this case is the energy and the frequency, right? And then the frequency directly influences how much energy there is because H is constant, like mathematically speaking. We can in fact derive this later. This E equals to H C lambda. We can actually derive this. So we know the formula C, which is the speed of light, is equal to lambda times V. So what does this mean? It tells us that the speed of light is directly proportional to both the wavelength and the frequency of the particle or the light, right? So what does that mean? Well, what this tells us is that since C is constant, right? If C is constant, if we have a bigger wavelength, so what does that tell us? Right? Since C stays constant, if we have a longer wavelength, it tells us that there's going to be a shorter frequency, and it's vice versa. If we have a higher frequency, we're going to have a shorter wavelength. So what does that look like graphically? Well, I can draw a diagram here that shows what's happening. So if I draw a wave like this, so the wavelength is the distance between the one peak and another peak. So we call this lambda, right? So as you can see, if we have this is like let's compare this to another thing first, right? I'm going to draw something like this, right? So if you compare these two, so below, right, we have lambda as the wavelength or the distance between two peaks, right? So as you can see here, when we have a bigger lambda or like a longer wavelength, right, the frequency is shorter. And then when we have a shorter wavelength, the frequency is much higher. Like that's just how light works, right? Because c is the thing that stays constant. That's the thing. Like light always travels at the same speed, no matter what. So that has to stay constant. So mathematically speaking, that makes sense. Like when you have a higher frequency, you have a shorter wavelength. When you have a higher wavelength or a longer wavelength, you have a shorter frequency. So now we know this formula. So what can we do with this formula, right? Well, we can manipulate, right? We can move the frequency to one side. So this is gonna be c divided by lambda. And now we can plug this into our equation, E equals to h times frequency, right? You can plug it in here. So this is going to be h times c divided by lambda. So this is going to be our equation, hc over lambda. So what exactly does this tell us? Right here, right? So what do we have in the equation? We have the Planck constant, we have the speed of light, we have the energy, and the wavelength. And then again, since the Planck constant and speed of light does not change, it tells us that E is also directly proportional to the wavelength. So in this case, a shorter wavelength will correspond to a higher energy, and a higher wavelength will correspond to a lower energy, right? Since hc doesn't change, if at the bottom is a smaller number, you get a higher energy on the output. Like mathematically speaking, that is correct too, right? So that's what this tells us, is that the energy is also directly proportional to the wavelength. And now we can move on to the next part. So the electromagnetic spectrum can be divided into a number of regions. So as we can see here, the regions go from radio to gamma ray. So this is talking about the wavelength. So a radio would be something like this, right? It has a very long wavelength and very low frequency. Whereas in a gamma ray, the wavelength will be much higher. It always, I probably couldn't draw it here, but you get the idea here. It will have a way higher frequency, and then it goes from radio, infrared, visible, ultraviolet, X-ray, to gamma ray. And then the units you can see here, an A symbol is called angstrom. So it is equal to 10 to the power of -8 centimeter. And all the colors we see are in fact from the visible spectrum, right? And then they correspond to wavelength, right? You can have the violet is the one that has the shortest wavelength, and the red is one that has the highest wavelength. So basically, all these light, right? These photons, their wavelength, we categorize them into these regions. So there's gamma rays, there's radio waves, there's all sort of different things. So now if I ask you a question, like you look at the visible spectrum, what we have here. Well, let me ask you then which color has the highest energy? And then it's the most energetic. So I'm gonna give you 5 seconds to think. Well, it's violet, right? Because remember, what you have just wrote down is E equals to hc divided by lambda, right? It's gonna be violet because lambda has the shortest wavelength out of all of these colors. So it's gonna make it have the highest energy. So that's the answer to our question here. But this is like a brief introduction to the electromagnetic spectrum and the regions they have and the colors they have. And in my next video, I'm gonna go into detail about these.